Our next section, 9-4, is looking at collision and impulse. So whenever you have a collision, two objects colliding, hitting each other, the momentum of a particle can change, right? A simple example of this is a baseball bat striking a baseball. Right? The bat exerts a huge amount of force on the ball, so that the ball that's initially being thrown perhaps 90 miles per hour at the plate can suddenly be moving in the opposite direction. That takes a lot of force. You can even see that with how the ball will deform slightly. Even the bat will deform slightly during this impact. And there's a link here, I'll put it in the comments as well, to some slow motion videos of golf balls being stricken in super slow motion. And you can see how the golf ball, which is such a rigid object, does actually deform along the side of the club and then springs outward and stretches out. So pretty wild. But the point is that when we have this force being applied to a ball or some other object, the momentum of it can change. And so we can write that mathematically in terms of something called the impulse, which for impulse we use a capital J. This is not joules, unfortunately. Bummer. I'm not sure why it's J, but there we have it. It's J with a vector for context. And so we define this quantity impulse as the integral of the force over the time. So that force acting over the entire time that it was acting. Now, once we define that, if we say that, hey, this force is an external force, we can remember from 2 sections ago that we got an equation for net external force, and we could relate that to momentum, right? That the F net is equal to dp dt. So if we plug that dp dt into this equation, then our dt's will cancel, and now we're just integrating over dp. In other words, we're just getting the change in momentum. And so that's what this equation shows down below, that the applied impulse is just going to be equal to the change in the momentum of the object during the collision. That's a simpler way to write it. Now, for both of these, the equations can be rewritten component by component, like other vector equations. So you can look at just the x components, just the y components, totally separate of each other. And another way of visualizing the equation that I find a little easier to see sometimes is you could imagine that you have a graph of force on the vertical scale versus time. And the force might not be constant here, right? As the bat is striking the ball, it initially is barely touching. So there's barely any force, but then as it's deforming, right, as they're smushing, then that's a huge amount of force, and it becomes less and less as the ball springs off the bat. And that's about what this shows, right? Where there's very little force initially, and then a huge amount of force, and then less and less force as the ball moves away from the bat. And the impulse is going to be the area under this force curve. So if you integrate the force with respect to time, then you'll get the impulse. And thus, also, if you know the area under the curve, you will get the change in momentum. So that's pretty cool. And this works for these variable forces as shown here. Now we can simplify it if, instead of knowing the exact force function as a function of time, if we just know the average force, right? So, okay, during this time interval, delta t, we know the average force is somewhere in between, right? Maybe if the max force here is 10, maybe the average force is something like 4.5. If you know the average force, then it will give you the same area under the curve. So it gives you the same impulse. You could calculate the impulse with just the average force times that delta t. And so since we're integrating, we only need to know the area under the force curve, and it's a lot easier to get this area, which is just force times time, than the area of the purple squiggly do. Not actually that squiggly, purple bump. So these are the equations that we'll need in order to understand the ideas of change in momentum, impulse, and forces. Now we're going to see how they can apply to a pretty interesting scenario, this checkpoint. A paratrooper whose chute fails to open lands in snow. He is hurt slightly. Had he landed on bare ground, the stopping time would have been 10 times shorter and the collision lethal. How does the presence of snow affect the paratrooper's change in momentum, the impulse stopping the paratrooper, and the force stopping the paratrooper? I gotta say, this one is a really good one to think through. This is one that usually students go back and forth on and have great discussions. So please do take some time to think this through. Make sure you write down an answer to part 1, 2, and 3 before you move on. So I'm gonna give you a moment to pause now. Okay, assuming you paused, we can take a look. So for the change in momentum, the impulse, and the force stopping the paratrooper. Let's talk it through before I show the answer. For the paratrooper's change in momentum, the key here is we can focus on the change in momentum of before encountering the snow or the ground and after the paratrooper stops, right? We're here talking about the collision with the ground, so we're focused on after he stops. So after colliding with the ground, the paratrooper is not moving, no momentum. But before encountering the snow or the ground, the paratrooper is moving with whatever his terminal velocity is and times his mass. So that means the momentum before encountering the snow or ground is going to be the same in either case, and the momentum after will also be the same in either case, right? In either case, he's stopping. So going from having max momentum to no momentum. So that one doesn't change. And that tells us then about the impulse stopping the paratrooper, because we know that the change in momentum needs to be equal to the impulse based on that impulse momentum theorem. So the impulse stopping the paratrooper is going to stay the same, which leaves us just the force stopping the paratrooper. How will that compare? Well, if we have the same impulse, but the stopping time is now much greater in the snow, then if impulse is equal to force times time, impulse is the same, time is greater, well, that tells us that our force is going to be less in the snow to keep the impulse the same. Oops. And there we have it, that the force is decreased. And this is good news, right? We want there to be less force pushing up on the paratrooper as the paratrooper is stopped, right? It's not the stopping that'll kill you, it's the force, how much time it takes to make that stop. And that's what airbags do. They slow down the collision, they make it take more time before you stop so that there's less force acting on you in those incidents. All right, hope that that makes sense. I'm happy to discuss it further if you still have questions with it. So otherwise, we will pause there. See you